Stoichiometry is a branch of chemistry that deals with the quantitative relationships between the reactants and products in a chemical reaction. It is the art of measuring chemical reactions, ensuring that all atoms balance and nothing is lost. This discipline is crucial for anyone who wants to understand how substances interact, transform, and even how they can be manipulated to yield desired outcomes. Whether you are a student, a hobbyist, or a professional in a laboratory, stoichiometry is your key to unlocking the secrets of chemical reactions. Understanding stoichiometry opens up a world of possibilities. It allows scientists to predict the amounts of substances consumed and produced in a given reaction. This knowledge is essential not only in academic settings, but also in real-world applications like drug manufacturing, environmental science, and food production. The precision required in stoichiometry ensures that chemical processes are both efficient and economical, reducing waste and maximizing yield. The term stoichiometry is derived from the Greek words stoichion, meaning element, and metron, meaning measure. This etymology reflects the essence of stoichiometry, the measurement of elements. By mastering this subject, we gain the ability to measure and control chemical reactions, which is a fundamental skill for any aspiring chemist or anyone interested in the sciences. In essence, stoichiometry is the chemistry equivalent of a recipe in cooking. Just as a chef follows a recipe to create a dish, a chemist uses stoichiometry to predict the outcomes of chemical reactions. This comparison to cooking makes stoichiometry more relatable and emphasizes its importance in both scientific and everyday contexts. At the heart of stoichiometry lies several key concepts: the mole, molar mass, and the law of conservation of mass. These foundational ideas allow us to understand and predict the outcomes of chemical reactions. The mole is the chemist's way of counting particles, much like a dozen represents 12 items. A mole represents approximately 6.022 times 10 to the 23rd particles, be they atoms, molecules, or ions. This large number is known as Avogadro's number and is central to converting between atoms and grams. Molar mass, on the other hand, is the mass of 1 mole of a substance, typically expressed in grams per mole. It is calculated based on the atomic masses of the elements in a compound. For example, the molar mass of water, H2O, is about 18 grams per mole, as it consists of 2 hydrogen atoms, each approximately 1 gram per mole, and 1 oxygen atom, approximately 16 grams per mole. Understanding molar mass is crucial for converting between mass and moles, a frequent requirement in stoichiometric calculations. The law of conservation of mass states that mass is neither created nor destroyed in a chemical reaction. This means that the total mass of reactants must equal the total mass of products. This principle is the bedrock of all stoichiometric calculations, ensuring that chemical equations are balanced and that no atoms are unaccounted for during reactions. Together, these concepts form the pillars of stoichiometry. They provide the necessary tools to analyze and predict chemical reactions accurately. Grasping these ideas is the first step toward mastering stoichiometry, enabling us to apply these principles in various scientific and industrial processes. Balancing chemical equations is a critical step in stoichiometry. It ensures that the law of conservation of mass is upheld, meaning the same number of each type of atom appears on both sides of the equation. To balance an equation, one must adjust the coefficients, the numbers before molecules or atoms, to get the same number of each atom on both the reactant and product sides. Consider the simple reaction of hydrogen burning in oxygen to form water. H2 plus O2 yields H2O. This equation, as written, is not balanced because there are 2 oxygen atoms on the reactant side and only 1 on the product side. To balance it, we adjust coefficients. 2H2 plus O2 yields 2H2O. Now there are 4 hydrogen atoms and 2 oxygen atoms on both sides, making it balanced. Balancing equations can sometimes be challenging, especially with complex reactions. However, there are systematic methods to tackle them. One approach is to start by balancing the atoms of elements that appear in only one reactant and one product first, leaving more common elements like oxygen and hydrogen for last. This strategy simplifies the process and makes it easier to spot discrepancies. Practice is key to becoming proficient at balancing equations. As you gain experience, it becomes more intuitive and you develop a better eye for the necessary adjustments. Remember, balancing equations is an essential skill not only in stoichiometry but also in understanding the chemistry behind reactions. Stoichiometry calculations follow a series of logical steps that convert known information into desired quantities. Let's explore a straightforward example, determining how much oxygen is needed to completely react with 10 grams of propane, C3H8, to form carbon dioxide and water. First, write the balanced equation, C3H8 plus 5O2 yields 3CO2 plus 4H2O. Next, calculate the molar mass of propane, which is approximately 44 grams per mole. Convert grams of propane to moles. 10 grams times 1 mole over 44 grams equals 0.227 moles of C3H8. Using the balanced equation, determine the moles of oxygen needed, 0.227 moles. C3H8 times 5 moles. O2 over 1 mole C3H8 equals 1.135 moles O2. Finally, convert moles of oxygen back to grams, 1.135 moles. O2 times 32 grams over 1 mole. O2 equals 36.32 grams of O2. Therefore, 36.32 grams of oxygen are needed to react with 10 grams of propane. This step-by-step approach ensures clarity and accuracy in calculations. Understanding these steps is crucial, because it allows chemists to predict the quantities of reactants required and products formed, which is vital for efficient chemical production. Practicing with varied problems enhances problem-solving skills and deepens understanding of the stoichiometric process. Section 5. Stoichiometry in Industry and Everyday Life. Stoichiometry extends far beyond the classroom, playing a vital role in various industries and everyday activities. In the pharmaceutical industry, it ensures the precise mixing of ingredients to produce safe and effective medications. Accurate stoichiometric calculations ensure that drugs have the correct dosage, avoiding potential side effects or inefficiencies. Industrial production also relies heavily on stoichiometry. In the manufacture of fertilizers, for instance, accurate stoichiometric calculations ensure the correct nutrient balance, maximizing crop yield, and reducing environmental impact. This precision is vital for sustainable agriculture and food security, highlighting stoichiometry's role in global health and economy. In our daily lives, stoichiometry is at work every time we cook. Recipes are akin to chemical equations where ingredients must be measured accurately to achieve the desired flavor and texture. This analogy helps to appreciate the omnipresence of stoichiometry and its practical relevance. Moreover, stoichiometry is crucial in environmental science for monitoring and controlling pollution. By understanding the chemical processes that occur in nature, scientists can develop strategies to mitigate harmful effects and promote sustainability. This application underscores the importance of stoichiometry in protecting our planet. Section 6. Tips for mastering stoichiometry. To master stoichiometry, one must start with a solid understanding of the basics. It's really important to familiarize yourself with the periodic table and the concept of moles and molar mass. These tools, are essential for making accurate conversions and calculations. Practice with simple problems before gradually tackling more complex scenarios to build confidence and competence. Visual aids can be extremely helpful. Use diagrams and flowcharts to map out the steps involved in stoichiometric calculations. This visualization aids in understanding relationships between quantities and enhances memory retention. Additionally, explaining concepts to peers or teaching them can reinforce your understanding and reveal any gaps in knowledge. Develop a systematic approach to solving problems. Consistency in your methodology reduces errors and improves efficiency. Identify any patterns or shortcuts that work best for you, and keep practicing to refine your skills. Don't hesitate to seek help from teachers or online resources when faced with challenging problems. Finally, stay patient and persistent. Stoichiometry may seem daunting at first, but with time and practice it becomes manageable and even enjoyable. Celebrate small victories along the way to stay motivated and remind yourself of the progress you've made. Section 7. Common mistakes and how to avoid them. In the journey of mastering stoichiometry, beginners often encounter common pitfalls. One frequent mistake is neglecting to balance chemical equations before performing calculations. This oversight can lead to incorrect results as the stoichiometric relationships depend on a balanced equation. Always double-check your balanced equation before proceeding. Another common error is miscalculating molar masses by forgetting to account for all atoms in a compound. This mistake can be avoided by using the periodic table to verify atomic masses and double-checking calculations. Consistent practice with calculating molar masses can help build accuracy and speed. Failing to convert units correctly is another trap for newcomers. Always ensure that units are consistent throughout your calculations. Converting grams to moles or moles to molecules requires precise unit management. Developing a habit of writing units next to numbers can prevent such errors. Lastly, rushing through problems without understanding the steps can lead to confusion and mistakes. Take time to understand each step in the process, and don't hesitate to revisit foundational concepts if needed. Patience and attention to detail are key to mastering stoichiometry and minimizing errors. Section 8. The role of stoichiometry in education. Stoichiometry plays a pivotal role in chemistry education, serving as a bridge between theoretical concepts and practical applications. It enhances critical thinking and problem-solving skills, as students must analyze and interpret data to solve stoichiometric problems. This analytical approach is valuable not only in chemistry, but in all scientific disciplines. In educational settings, stoichiometry serves as a foundational topic that prepares students for advanced studies in chemistry and related fields. Understanding stoichiometry is essential for grasping more complex topics such as thermodynamics, kinetics, and equilibrium. It provides a framework for comprehending how chemical reactions occur and why they behave in certain ways. Hands-on laboratory experiments involving stoichiometry allow students to see the tangible outcomes of their calculations. These experiments reinforce theoretical knowledge and provide an opportunity to apply stoichiometric principles in a controlled environment. Such experiences can spark interest in chemistry and inspire future scientists and engineers. Furthermore, stoichiometry is a tool for developing a scientific mindset. It teaches students the importance of precision, accuracy, and logical reasoning, skills that are valuable in any career path. By mastering stoichiometry, students gain confidence in their ability to tackle complex scientific challenges. Section 9. The future of stoichiometry in science. As science and technology continue to advance, the role of stoichiometry evolves alongside. With the advent of new materials and technologies, stoichiometry remains a critical tool for innovation and discovery. In the field of nanotechnology, for example, precise stoichiometric calculations are essential for designing materials with specific properties and functions. Environmental science and sustainability will increasingly rely on stoichiometry to develop solutions for global challenges like climate change and pollution. By understanding the chemical processes that govern our environment, scientists can create innovative strategies to reduce carbon emissions and promote ecological balance. In pharmaceuticals, stoichiometry will continue to play a crucial role in drug development and personalized medicine. As our understanding of genetics and biochemistry grows, stoichiometric calculations will aid in designing targeted therapies tailored to individual needs, improving health outcomes and quality of life. As we look to the future, stoichiometry will remain a cornerstone of scientific progress. Its principles will continue to guide researchers in their quest to unlock the mysteries of the universe, from the smallest particles to the vastness of space. Mastering stoichiometry today will prepare the scientists of tomorrow to tackle the challenges and opportunities that lie ahead.